All right. Good morning to the early birds, Chazel, Michael, Francis, Adriel, Leon Gray, Sheila, and Ezekiel. Last time we talked about ways on how to improve the numerical differentiation formulas that we obtained by using finite differences, which is a consequence of Taylor's theorem, right? So inimbestigahan natin yung isang anomaly na kapag ka pala pinagawa ko sa isang spreadsheet like Excel, or actually in any computing device or application, yung pina-implement natin yung numerical differentiation formula, there will be some breaking point wherein the method will underperform the theoretical expectations. So sinabi natin halimbawa, yung example na 3-point centered formula of order 2 na dinerive natin before the reading break, pina-implement natin kay Excel. We expected that the error will go to zero as fast as how h squared will go to zero, right? And then it happened for some values of h. And then theoretically, we expect na habang si h ay palapit ng palapit kay zero, yung error ay palapit ng palapit kay zero at the same rate that h squared approaches zero. Kaya lang nung dinrag natin yung formula kay Excel, nakita natin na oops, there is something going on, something fishy is going on kasi nag-underperform na yung method, hindi niya nasunod yung pag-vanish ng error kasing bilis ni h squared. Tapos worst case ay totally wrong na yung nakuha natin approximate for f prime. And we trace the reason back to machine precision. Ang problema kasi computers are finite devices. So at some point, after every calculation they perform, they will only retain a certain number of significant digits. Tapos kapag yung step size natin is far less than the number of significant digits kept by the application, posibleng magkaroon na ng mga error kasi natatruncate na yung mga significant digits, which is bad for us. And so to remedy that, to go around that, and this is a classic thing that numerical analysts do, ginagawa natin ay pina-factor in natin yung error due to truncation or due to round-off errors na ginagawa ng machine. So pag-derive natin ng method, may theoretical error. So kung perfect computational machine yung gagawin natin, which doesn't exist because all computing devices are finite in nature, or kung ipe-perform natin by hand, yung mga calculations, ito yung makukuha nating error, ito yung expected error. So kaya lang, pag in-implement mo siya sa machine, kailangan isama natin yung round-off error or the errors due to propagation of errors due to truncation and rounding off after every operation. Tapos with that knowledge, pinactor in natin siya dun sa framework natin. Tapos we found the optimal step size or we found an approximate for the optimal step size doon sa approximation. I see some people are leaving. Hindi pa ako nag-share ng screen, so nakalimutan ko siyang gawin. Baka nag-wonder kayo bakit wala kayo nakikita. So that's what we did last time. And then today we will try to discuss another important improvement of our numerical differentiation formula, which is called Richardson extrapolation. So yung ginawa natin last time, medyo local siya. Kasi ang ginawa nating improvement ay naghanap tayo ng step size para makuha natin yung optimal machine implementation ng method or near optimal machine implementation of the method. So isang H value lang yung concern natin. Ngayon, ang titingnan natin ay paano ko mas mapapabilis yung convergence nung sequence of approximations dun sa actual value. Kasi yung ginawa natin last time dun sa 3-point centered formula of order 2, alam natin na nagko-converge yung approximates natin sa derivative sa actual value as fast as how h squared approaches zero. So ngayon titingnan natin paano natin mas mapapabilis pa doon yung pag-converge nung sequence of approximates which are dependent on the step size h papunta dun sa actual value. So paglalaruan natin ngayon yung mga approximates na nakukuha natin using various values of h. So instead of say in our example last time, nakasing bilis siya ni h squared sa pag-zero, gagawin nating mas mabilis kaysa kay h squared. So yun yung plano natin gawin ngayon. But before we go there, one of your classmates would like to announce something. Chazel, you have the virtual space.
Ayan. Greetings everyone. I am Chazalinis Casanova, and on behalf of AMAT 199 Section T, under the supervision of Associate Professor Aleli Domingo, I would like to invite all of you to our upcoming webinar event with the theme Past, Present, and Future, the Old Script Meets the New Technology. This webinar will happen on Monday, 15th of November 2021, 9 o'clock a.m. via Zoom and Facebook Live. Our guest speaker, Mr. Rodney Pino from the University of Philippines Diliman and Baguio, will discuss their study entitled Optical Character Recognition System for Bayesian Scripts using Support Vector Machine. If you're interested, you can pre-register using the link you can find on the chat box that I'll be sending later. Certificates of participation will be distributed to the participants if they answer the evaluation form. Also, a big thank you to Sir Neil as he will be giving incentives if you attend the webinar. For more updates, you can check our official Facebook page, AMAT199-seminars. And if you have other concerns, you can send a message on our Facebook page or send us an email at amat199.externals@gmail.com or amat199.records@gmail.com. Thank you so much, and together let us unveil the relationship of the past, present, and the future. Thank you po.
Okay, salamat, Chazel. Yeah, so if you want, attend the session. Yung incentive ay pag-iisipan ko pa kung ilan, all right? Pero magbibigay nga ako ng incentive. Pero it's not just for attending. I want you to submit a short reaction paper or kung ano man yung gusto niyo. Walang page limit dun sa reaction about the event that you will attend. Tapos gagawa na lang ako ng submission bin kay Canvas para dun sa reaction paper, okay? So, 'yon. Hindi lang attendance pero kailangan niyo mag-submit ng isang short or long kung bahala na kayo na reaction paper. All right? So, Chazel already sent the link sa chat box so you can check it out. So, hold on. I'll start the formal discussion. Hold on, connecting pa yung second device ko. Okay, share screen. Okay. Okay, can you guys see my screen now? Hindi ko siya nakikita sa aking monitor. Pero how about you guys?
Kita na
Kita
po,
niyo?
sir.
All right, thank you. So as I've mentioned, we will be looking at the method called Richardson extrapolation. So ang idea dito ay i-implement di ba natin yung different numerical differentiation formula with a particular value of h. Halimbawa si d of the first step size. Ito yung i-consider natin na first approximate kay actual derivative, right? And then pwede mo kang pumili ng mas maliit na step size. So say call it H2, and then we get another estimate. And if we will implement the method in a perfect or in an ideal computing device, dapat kung si H1 ay mas malaki kaysa kay H2, then the approximation we get from H2 should be better. All right? Kasi nga habang lumiliit si H, dapat gumaganda ng gumaganda yung approximation natin sa derivative. So you can continue this process, kumuha ka pa ng isang H3, and so on. Pwedeng somewhere you get the near optimal step size, let's call it H sub O, na nakuha natin from the previous discussion. And then you do this for infinitely many values for H that will decrease to 0. Right? So H3 and so on. So idea is that the HNs will converge to 0 eventually. Okay. Now the idea here is if this happens, then the DH sub n's, the sequence of approximates we get, will converge to the actual value in a theoretical perspective. Meaning, in an ideal machine, dapat makuha natin yung actual value ng derivative as a limit of the sequence of approximates that we get. Kaya lang dun sa example natin last time, sabi ko nga, big O of h squared yung 3-point centered formula na nakuha natin. So, magko-converge papunta dun sa actual value, yung sequence of approximates, kasing bilis ng pagzizero ni h squared. Now, our goal is to use this sequence of approximates to generate another sequence, okay? Gagawa tayo ng isang formula na bagong formula para sa numerical differentiation pero involve yung mga approximates na makukuha natin from a simple implementation of the numerical differentiation formula that we derived, all right? Pero ang idea, yung bagong sequence na mako-construct natin using these approximations will yield another sequence of approximations that will converge faster than h squared to the actual value. Okay? So mas papabilisin natin yung convergence ng method. Okay? And before we go there, let's have a quick recap of the big O notations or the Bachmann-Landau notations. So sabi natin si g of h ay big O ni h to the k if in the long run a multiple of h to the k is an asymptote, is an upper bound of g of h. Meaning for large enough h or for small enough h's, depending on if you're doing infinite or infinitesimal asymptotics, dapat yung magnitude ni g of h ay bounded above by a multiple of the magnitude of h to the power k. Or in other words, hold on. Okay, sorry about that. So that's equivalent to saying that the limit of the magnitude of gh all over h to the k is bounded above by a constant c. So ito yung alternative definition ng Bachmann-Landau big O notation. Okay? So and then since we're doing infinitesimal, the h's we are considering approaches zero or they are decreasing to zero, kukunin ko yung limit nung ratio ng g of h at saka nung h to the k, and it will be bounded above by a constant. So yun yung ibig sabihin ng big O of h to the k. Magkasing bilis si g at saka si h nagko-converge to their respective limits up to some constant of proportionality c. Okay? Pero if it happened that the limit, this limit, is equal to zero, okay? So anong ibig sabihin nito? Can you interpret this for me? What happens when the limit, anong ibig sabihin na nag-zero yung limit ng gh over h to the k? Can anyone, can I get a volunteer? Ano yung ibig sabihin na yung limit ng gh over h to the k ay naging equal kay zero? Kahit intuitive lang, hindi nyo kailangan yung technical. So tingnan nyo lang, ano yung kailan mangyayari na yung ratio ay magkakaroon ng limit na equal kay zero? Or what happened? Why did we get a zero as the limit? Habang I'll try to restart my screen sharing. Okay, wala talagang volunteer. Okay, so the reason is or the interpretation why of this statement is that mas mabilis lumiliit or lumalaki yung h to the k. All right? So that means h to the k becomes larger than g to the h at a faster rate. Kaya ibig sabihin, mas malaki si h to the k, kaya yung ratio ay in the long run nagzi-zero. So definitely, mas mabilis by a significant margin lumaki yung h to the k kesa kay g of h. So that means g of h approaches zero much faster than h to the k. All right? And if this happens, we have another Bachmann-Landau notation for this. If this is true, then we say that g of h is a small o of h to the power k. So ang interpretation nito, mas mabilis nagko-converge si g of h to its limit than how h to the k approaches 0. So definitely, in the sense of infinitesimal calculus, mas gusto natin yung mga formulas o mga approximation techniques that converges with the rate of small o of h to the k than those that converge with the rate of convergence big O of h to the k. Tapos yun yung gagawin natin ngayon. Yung formula natin of order big O's of a power of h, gusto nating i-translate sila into a method of order of convergence little o of h to the k. Para ang interpretation naman doon, mas mabilis silang mag-converge kesa kung paano nagko-converge si h to the k papunta kay 0. Okay? And this is key. Pakitandaan nito. So to guarantee that the resulting formula would be of order small o or little o of h to the k, dapat yung limit na to ay mag-equal kay 0. Okay? Now, to illustrate this, tingnan natin balikan natin yung 3-point centered formula that we considered last time. Medyo suki na natin itong i-analyze. So remember, we derived this formula before the reading break. We computed the optimal step size or the near optimal step size for the machine implementation of this method. Now let's try to improve it by accelerating the order of convergence. Okay. Now, para makuha natin or pag kinonsider natin tong formula na to, right? So si D yung actual derivative, si D of H ay ito. Okay, so maybe I should encircle that. Ito si D of H kasi siya yung estimate natin para kay D obtained by using step size H. Function siya ni H kasi si H ay involved dito. Remember, si X dito ay fixed kung saan natin gustong i-approximate yung derivative. Okay? So this is our D of H. And if we compute the limit of D minus D of H, so this is the this is the absolute error, right? So gaano kalayo yung approximate using step size H kesa kay D, tas divide natin by H squared because we know that the error that this is a big O of H squared. Okay? So gawin natin. So ibig sabihin yung D minus DH, ito lamang yung error term dun sa numerical differentiation formula. So D minus D of H will be equal to this guy. H squared over 6 times F triple prime at C, where C is a number between X minus H and X plus H. All right? I-divide natin siya by H squared dun sa loob ng limit. So madi-divide to by H squared. So the H squared above will be canceled by the H squared below. And ultimately we'll have this 1/6 F triple prime of C. And then we take the limit as H approaches 0. The thing here is that independent na to of H. So this could be treated as a constant, right? F triple prime of C will just be a constant, or it will be bounded by a constant because F is continuous, or F triple prime is assumed to be continuous kasi si F ay assumed na smoothed infinitely many times. So that ibig sabihin si F triple prime ay continuous, nasa interval x minus h to x plus h tayo. So the extreme value theorem guarantees na there is a constant C, right? Na totoo yan. Okay? Or there is a maximum bound for this guy. So that means this is this is a constant. And you can tell from this limit evaluation that indeed the order of convergence of this formula is big O of h squared. Kasi yung limit nitong quotient na to ay equal or bounded by a non-zero constant. Okay? Now, bakit ko pala nasulat dito na equal siya kay C? Well, remember kay F triple prime of X. Why was I able to exchange C by X? Well, the thing there is, remember that C is a number between X minus H and X plus H. We don't know what happens or what is the exact value of C. Alam lang natin kung saang interval siya nakatira. Pero remember, in this limiting process, we are taking the limit as H approaches 0. So kapag ka si h ay nag-approach ng 0, so x minus h will be arbitrarily close to to x, and x plus h will also be arbitrarily close to x. So parang isa lang siyang neighborhood. So shout out sa mga nagmamath 155 dyan. So meron ka lang open neighborhood mula kay x minus h hanggang kay x plus h. So habang lumiliit si h, ibig sabihin yung x minus h palapit ng palapit kay x, yung x plus h palapit ng palapit kay x. So essentially, c would be equal to x in the limit. Okay, habang lumiliit yung interval, isa na lang yung nakukuha nating element ng open interval. Okay? Or sort of. So, ganun yung idea. Kaya ako nasulat yan. So, kung gusto nating i-accelerate yung method o yung order of convergence of nung method faster than how h squared approaches 0, gusto natin itong limit na to, itong limit na to ay mag-0. We cannot do anything about the denominator, so I'll retain the denominator. And so if we want the limit of the quotient to approach 0 or to be equal to 0, I want the numerator to go to 0. Okay? So ang idea ay, alam ko na ang d minus dh, pag sinimplify natin, ang sagot ay negative h squared f triple prime of c. But I want this guy to be equal to, hopefully, gusto ko siyang mag-0. So kung meron na akong d minus dh, tapos ang difference nila ay minus h squared f triple prime of c, then I could add this guy dun sa numerator. Parang dinadaya ko siya. Alam ko na kasi yung d minus dh. Yung d minus dh ay ito. Gusto ko yung numerator dun sa loob ng limit ay mag-0. So dadayain ko ngayon. So dadagdagan ko siya ng either positive h squared over 6l f triple prime of x, which is this guy, okay? Or pwede rin namang f triple prime of c all over 6. Para ito, sure tayo ay mag-0 siya talaga. Okay? And true enough, if you take the limit of this entire thing with this additional term here, which it seemed out of the blue, pero hindi. Dinaya natin siya. Alam ko kung ano yung i-add or isusubtract sa numerator para mag-0 siya. So, if we will retrace the steps, then this will just become, so meron tong h squared, pero magkakaroon ka na lang ng f triple prime of x minus f triple prime of c. But we have noted earlier that as h approaches 0, f triple prime of x and f triple prime of c will be the same thing. So this guy will vanish, giving us the limit equal to 0. Okay? So yun pala yung gusto nating mangyari. Para magkaroon tayo ng small o na formula, yung error term, remember yung numerator dito represents the error term. Yung error term nung differentiation formula na i-develop natin dapat equal sa d minus dh plus h squared over 6 plus f triple prime factorial. F triple prime of x. So this is what I want to be my error term, all right? So that means si d of h or si actual value ng derivative ay dapat maging equal kay d of h plus h squared over 6 f triple prime of x. Okay? Kasi ito yung error term. Kasi yung error term, remember, it is the actual minus the approximate. Okay? So, actually, dapat pala ito ay minus. Okay? So, from here, dapat, ito yung actual. Kung ano man yung minus natin, ito dapat yung approximation natin. Right? Para siya yung maging error term talaga. So, that means d of h or d must be equal to dh minus h squared over 6 times f triple prime of x. Ito yung gusto nating approximate. Kaya lang, alam ko na kung ito yung formula ko, ito ay mag-converge faster than h squared. Pero ang problema, hindi natin ito magagamit at its current form kasi wala tayong data about f triple prime of x, right? So remember, ang inassume natin dito, ang data lamang natin ay si x at saka si f of x. So we need to get rid of f triple prime of x here to get a sensible formula that we can implement based on the availability of the data. So ito yung isang usual technique. Mandadaya na naman ako. Paano ko to gagawin? So tapos na sana kung alam ko yung f triple prime. Pero usually we don't have any access to the third derivative of a function. So kasi nga first derivative yung ina-approximate natin. So malamang hindi natin alam kung ano yung third derivative kasi si first derivative pa lang hindi na natin alam. So kailangan kong humanap uli ng loophole o ng clever way on how to get this approximation formula. So what I'll do here is that actually ito pala ay approximately equal lang. Pero yung error dito ay small o of h squared. Alright? Mas mabilis kay h squared siya nagzi-zero. Okay. Now ito yung trick na gagawin ko. So d is equal to this guy. Alright? Tinawag ko lang yung -1/6 f triple prime of x as k1. Okay? But again, we don't have any knowledge about K1 or the value of K1. So somehow I want K1 to be eliminated, okay? Or mawala siya somewhere along the road. So what I'll do here is, remember ano yung sabi ko kanina dun sa introduction? Gusto kong gamitin yung ibang mga approximates using a simple formula, pabibilisin ko lamang yung convergence. So I will assume that I have a priori implementation of the basic formula that we derive from Module 6 using various step sizes. Tapos sila yung gagamitin kong input dun sa Richardson extrapolation process na magbibigay sa akin ng isang sequence of approximates na mas mabilis yung convergence. Okay? So, ibig sabihin, pwede ko pala itong paglaruan, pwede kong palitan yung value ni h. Halimbawa, a common choice is kalahatiin ko kaya ngayon yung h. So if I will make kalahati, so kanyotic, pero kung kakalahatiin ko yung step size, lahat ng h's dito, pwede kong palitan ng h over 2. Okay? So that will give us an approximation using the basic formula, but in that time, yung step size ay h over 2 na lamang. Tapos yung h dito, papalitan ko rin ng h over 2. Magkakaroon ako ng k1 times h squared over 4. And then here, sa big O, sa small o, yung h ay papalitan mo rin ng h over 2, so magiging h squared over 4. Pero kung tandaan nyo sa Bachmann-Landau notations, hindi nagma-matter yung scaling constants doon sa big O. So yung big O ni h squared over 4 ay big O pa rin ni h squared. Okay? And that's why it was retained here. Okay. Now, we have these two equations. You could have chosen to use h over 10, h over 7, h over pi, whatever. That's fine. It's just a common choice to always take half of the original h. Kasi kailangan nating maging extra careful kasi kung matatandaan nyo sa numerical implementation, pag napasobra yung liit ni h, ay magfe-fail yung machine implementation ng algorithm. So kaya medyo pahinay-hinay ko siyang babawasan. Kaya usual choice ay h over 2. Pwedeng h over 100, kaya lang baka lampas na yun sa number of significant digits carried by your computing application. Okay? So h over 2. And then the next step is to subtract the second or the corresponding sides of the second equation from the first equation. So if I do that, we'll have this. 0 equals dh minus dh over 2 and so on. Okay? And then arithmetic lang yung algebra lang yung subtraction ng unang dalawang terms. Pero yung big O of h squared minus big O of yung small O of h squared minus small o of h squared ay small o of h squared pa rin. So hopefully tandaan nyo pa from AMAS 152. If you forgot the arithmetic of the Bachmann-Landau notations, meron din dun sa Vortex. May isang chapter doon or isang section dedicated to Bachmann-Landau equations or notations. So you can review that there. But essentially, we get this. And then I will isolate K1 to one side. Kasi remember, si K1 yung wala tayong access kasi siya yung -1/6 f triple prime of x. So I want to get an expression for K1. Kaya pinipare ko na siya si K1 o yung term na may K1 ay in-isolate ko dito sa kaliwa. Okay? So yan yung mangyayari. And then remember what is our approximation formula? Okay, remember we said D is equal to DH plus K1H squared plus small of H squared. Ito yung target formula natin. But we cannot use this kasi nga hindi natin alam si K1. Pero this time, I have an expression for K1 times H squared involving only previous approximates. So in this template, I can now replace K1 by this guy. So kung gagawin ko yon, okay, pwede kong ibaba ito. Tapos si K1 H squared, mapapalitan na siya ng 4/3 times D of H over 2 minus D of H, and so on. And this is fine because D of H over 2 is the result of the implementation of the simple formula, but this time using step size H over 2. And then if you are patient enough and perform the algebraic manipulations here, you will get this guy. That the actual derivative is equal to 4 times the approximate using half the step size minus the approximate using the step size h all over 3 plus little o of h squared. Now, this formula will require us to use two approximations. Pero ang kagandahan dito, yung sequence na makukuha natin with this approximation is guaranteed to converge faster than the simple implementation of the method. All right. Now, I think we are now ready to look at the machine implementation of this Richardson extrapolated formula. But before that, do you guys have any questions? I hope yung process ay clear. Kasi sa lab exer, papagawan kayo ng Richardson extrapolation formula. Kasi pwede nyo itong i-apply sa kahit anong numerical differentiation formula galing sa finite differences in the same fashion. Ganito rin yung process na gagawin nyo. But kaya importante na mag-gets nyo or maintindihan nyo kung paano yung mga or paano ginawa yung derivation at bakit pwede natin gawin yung bawat steps na yon. Okay? Any questions? Everything's clear? Can I see some thumbs up or some reactions if that's clear? All right, thank you guys. Oh, by the way, before I shift to Excel or to my spreadsheet, itong formula na to ay mag-hold sa kahit na anong formula of order h squared. Hindi necessarily numerical differentiation formula, pero halimbawa sa ibang AMAT courses nyo, naka-encounter kayo ng optimization technique na iterative in nature. Tapos nakita nyo na ang order of convergence nung optimization routine nyo ay big O of h squared. Pwede nyo itong gamitin. So yung D of h, yung approximate nyo using h over 2. And then ito yung approximate nyo using step size h. Madali lang. 4 times yung approximate using the smaller step size minus the approximate using the larger step size all over 3. Yung bagong sequence na makukuha nyo, magko-converge ng mas mabilis kaysa kay h squared. So kung nag-ESP kayo or nagti-thesis, medyo nababagalan kayo dun sa convergence nung ginagamit yung method na order 2 pala siya, gawin nyo lang itong simple extrapolation process na to, mas bibilis yung yung convergence nung method nyo. So hindi siya limited sa numerical differentiation formula. You can exchange D here by any formula or any iterative formula of order h squared. Okay? Now, example 7.2 will ask us to implement this process using, with respect to this function, e to the x, in evaluating its derivative at x equals 0. Well, it's fine. We know the exact value here is 0. Pero gamitin natin or illustrate natin itong process na to. Okay? So I'm gonna Shift to my spreadsheet here. Okay, there you go. Okay. I hope kita nyo na guys yung Excel ko. Alright, so we start with 0.1. Yan yung una kong step size na gagamitin. 3C2, abbreviation ko lang sa 3-point centered formula of order 2. First number represents the number of points used. Second ay central or centered. It could be forward or it could be backward, pero yung example natin ay centered. Tapos yung last digit siya yung order of convergence. So it's a big O of h squared. And then the formula is, remember, it's e to the 0 plus h minus e to the 0 minus h all over, oops, kulang ang parentheses, all over 2 times h. Okay. At ito yung nakuha nating approximation from last time. And then we can also calculate the relative error or the absolute error. So that's the absolute value of the approximate minus the actual value 1. And there you go. Ito rin yung figure na nakuha natin from last time. And again, the extrapolation process we designed admits approximates or requires approximates with the step size being half every step of the way. So kalahatiin ko yung step size. So divide ko lang by 2 yung previous step size. Enter. And then I'll drag this formula para makita natin yung susunod na approximate. And I'll also drag the error formula. We see this. Tapos kung makikita nyo, ano dapat yung ina-expect kong ratio between these two errors? So nangyari dito ay si h, dinivide ko by 2. So ano yung ina-expect nating behavior nitong error? So yung error dapat ay madidivide by what constant? Anyone who would like to try? Ano yung ina-expect ko? Bawal kayo mag-calcu pero knowing that it is a formula of order h squared, I divided h by 2. So by ilan dapat madidivide yung error? Sige nga, kung tandaan niyo yung pinag-aagawa natin last time.
Edi 1/4 ba, sir?
Okay, who's that? Sorry, hindi ko nakikita pag naka-full screen.
Si David po ito.
Okay, thank you, David. Yeah, that's right. Mamumultiply ng 1/4 o madidivide by 2. Kasi nga, ito ay h over 2. So yung h squared ay magiging h squared over 4. Right? So ibig sabihin, madidivide siya by 4. And true enough, if you get the quotient, this guy divided by this guy, makukuha ko ay around 4. Okay? Kasi nga, big O of h squared siya. Hindi eksaktong 4 yung makukuha natin because this is a big O of h squared. So asymptotically bounded siya by a multiple ni h squared. So it could be a factor of 4, pero true enough, it's around 4. And then if I continue this process, drag ko lang si Excel. Kaya maganda yung Excel sa numerical differentiation kasi drag lang tayo ng drag. Okay? Tapos i-drag ko to. Makukuha ko yung estimates. And then I'll take the ratio just to verify that this is a big O of h squared. Kung makikita nyo yung mga ratio between two consecutive errors is around 4 or around 1/4 kung paano nyo ginawa yung division. Okay? So basically, yeah, we're convinced that everything worked well here in this example. Kasi hindi ko naman tinaasan yung masyadong binabaan yung h. Pero expect nyo pag binabaan ko pa si h ng todo, baka magkaroon na ng pumasok na yung machine precision. Okay? Because remember, Excel only keeps 15 significant digits after every calculation. So, pero dito 10 to the minus 5 lang naman yung pinakamaliit ko na h. So everything will work fine here. Hindi pa magki-kick in or hindi pa significantly ma-factor in yung round-off error. Okay? Now apply Richardson extrapolation formula that we derived. So siya yung nasa column ng RE formula. So remember from the module, we know that the formula would be this. Equal siya sa 4 times yung estimate galing dun sa kalahating step size, so siya yung nasa forward, minus yung approximate using the original step size by 3. So napakasimple ng ginawa ko. Kinol ko lang yung dalawang magkasunod or ginamit ko lang yung dalawang magkasunod na approximates. And there is a linear relationship or a linear calculation that I need to perform, which is not that difficult to do. And this is the new estimate that I will get using the extrapolated formula. And then if we will compute the absolute error, so the RE estimate minus the actual value, and then we get an error of just 2.08 times 10 to the negative 7. All right. And that is a very big improvement from what we would have gotten with 2 steps of the normal formula. So normal formula, yung error using the first method, using the first step size, ay 1.6 times 10 to the minus 3. Tapos yung pag kinalhati ko yung step size, 4.2 times 10 to the negative 4. Pero pag nag-Richardson extrapolation ako gamit yung dalawang estimates na to, I get a far better formula, which is 2.08 times 10 to the negative 7. And then I can drag this. Okay. Ito na yung series of approximations na pwede ko makuha using Richardson extrapolation. Now, bakit hanggang dito lang yung dinrag ko? Ba't hindi ko sinama itong yellow cell na to? Any idea? Anyone aside from David? Guys, sayang yung recitation points. Anyone? Bakit hindi ko dinrag hanggang dun sa yellow portion yung formula? Kung wala kayong microphone or ayaw nyo magsalita, pwede naman lang. Comment sa chat box. But I see Ezekiel's bubble is lighting up. Are you trying to speak, Ezekiel?
Sir.
Yes.
Na-disconnect po ako, sir.
Okay, no worries. Yeah.
Sorry, sir.
No problem. Yeah. Akala ko lang nag-recite ka, hindi ko naririnig. Sinong gusto mag-try? Come on, guys. Talagang monologue ang ginagawa ko sa inyo, no? So, magtawag kaya ako next time, randomly. Magkaroon tayo ng raffle ng fishbowl dito. Kaya lang problema ko, baka hindi nyo na ako attendance. So, yon. Okay, but anyway, I cannot drag the formula until the yellow square because if I do so, i-drag ko yan. Okay? Bakit maling-mali? Kasi makikita nyo, kailangan ko yung nandito sa cell 18, nasa cell B18, para dun sa Richardson extrapolation. So kung gusto kong abutin siya dito or kung gusto kong makuha yung RE approximate for this part, kailangan kong i-drag. Kumuha pa ako ng isang approximate using the centered formula. Okay. Hindi ko pala na-drag yung step size H. Okay. Then I'll get this. Okay. Pero tinigil ko siya dito kasi hindi na nag-further improve yung error. Actually, nag-improve pa pala siya from 9.9 times 10 to the negative 11 down to 2.2 times 10 to the negative 11. Right? So let me just kill this cells. So yan na lang. And then if we drag the relative errors, the absolute errors, ito yung makukuha natin. Okay? And then tingnan natin yung ratio between two consecutive errors. So this would be this guy divided by this guy or baliktad. Ito divided by this next one. Okay. So makikita nyo yung ratio between the current error and the next error is 16. Tapos pababa siya ng pababa, pero dito medyo hindi na maganda kasi medyo lumaki na yung error, bumaba siya ng 1.5, naging 1.8, and so on. But at least for the first few approximations, before numerical instability and round of errors kick in, mas mabilis na yung convergence niya talaga kesa kay H squared. Kasi in-expect natin kung order h squared pa rin siya, yung ratio between two consecutive estimates dapat ay pupunta na siya kay ay magiging around 4. Pero dito nakita natin around 16 na siya. Actually, I think it's much better to look at it this way. Equals the next one over the previous. Then this guys should dapat eventually magzi-zero yung ratio na yan. Okay. Pero yun nga, bakit hindi siya nangyayari? There might be some round-offs or instabilities that happened along the way. But the idea is, kung makita niyo sa graph na to, okay, pinlot ko yung absolute error, yung red one, yung blue one, ay yung error galing sa basic finite difference formula that we implemented, and then yung orange, siya yung error galing sa Richardson extrapolation. But again, we need to be very careful here kasi nga 15 significant digits lang yung nakikip dun sa aking calculation. So beyond that, medyo maging erratic na yung behavior ng error. Okay? So probably here you can stop at say nakita niyo yung ratio kanina nung consecutive errors. Okay. We expect something greater than 4 dun sa ratio. And then pag may nakita na kayong anomaly na medyo hindi na siya ganon nagpa-follow nung trend, pwede nyo nang itigil. So for instance, I could be happy with this approximation, right? Kasi after this iteration, mas lumaki yung error from 10 to the minus 13. Actually, mas lumiliit pa rin pala siya, pero yung pagliit ay hindi na ganun ka-significant. Okay? Konti na lang yung improvement na nakita natin from here until the end. So dahil hindi na masyadong nagkakaroon ng improvement dun sa estimate, I can say na, okay, I will settle with this estimate for f prime of 0 because the Richardson approximate has an absolute error of 1.52 times 10 to the minus 13 na. Compared to the approximation using the 3-point centered formula of order 2 na ang relative error, ang absolute error lang ay 1.6 times 10 to the minus 6. So that's how Richardson extrapolation improves the numerical differentiation formula. It's more of playing with different values of h. So ginagawa nating mas mabilis nagko-converge yung estimate kesa dun sa finite difference formula na dinerive natin. Okay? Now, any questions, guys? I think that's it for us today, unless you have some questions. Okay, dahil may konti pang time, let's browse the lab exercise a little bit. Okay. Tingnan natin kung anong pinagawa ng lab instructors nyo. Hindi ko na lang sasabihin kung sino yung nagawa nito. Baka i-bash nyo siya. Pero anyway, so first bullet or first item, derive a 4-point backward formula. Bakit both of order 2 for f prime? Siguro wala dapat both. So kailangan lang ng 4-point backward formula of order 2 para kay f prime. Okay? And then sa part 2a, i-implement nyo lang yung method na yon using the data from this reference. Actually, ito na pala yung model niya. Inisip ko kasi kailangan niyo yung data. Pero ito pala yung model na nakuha ni Pearl and Reed para sa population ng US. And then ang gagawin natin ay gamitan yung formula na na-derive kay 1 to estimate the yearly growth rate. So kailangan yung evaluate si P prime at step size h equals 1 para makuha niyo yung yearly or annual growth rate. So kailangan nyo remember si 4-point backward, no? So kung gusto nyo i-approximate yung P1, kailangan nyo yung P of negative 1, P of negative 2, and P of negative 3. Alright? Para masatisfy yung pagiging backward ng formula. Okay? Madali lang itong gamitin kasi pwede nyo palitan yung T. It is a function of T. Just replace it by appropriate t-value. Okay? Makukuha niyo siya. Tapos sa letter B, ipaperturb niyo raw yung mga p-values. So may p-values kayo na makukuha mula sa substitution ng mga appropriate t-values dun sa model kay P. So ang gagawin niyo lang daw, ipaperturb niyo siya by a random number of order 10 to the... Okay, I need to double check with your lab instructors kung talagang 10 to the 4th dapat yung perturbation or 10 to the minus 4. Pero pwede rin kasing 10 to the 4th kasi ibig sabihin kukuha ka lang ng random number between what? Between negative anong 10 to the 4th? Ang 10 to the 4th ay 1, 2, 3, 4. Kukuha ka lang ng random number between negative 10,000 hanggang kay positive 10,000. Tapos i-add natin yun dun sa p-values, sa bawat isang p-values na kailangan ko. And that's fine as a perturbation because I'm imagining P, yung population value ng US ay in the hundreds of millions. So kaya baka okay na i-perturb siya by 10,000. But double check with your lab instructors kung talagang 10 to the 4th ito or 10 to the negative 4. Pero either way, I think 10 to the 4th is a nice perturbation. 10 to the minus 4 will be a very small perturbation kasi nga millions yung values ni P. So yung 10,000, kukunti lang yun compared to 10 to the 6. So it's about order 10 to the 2 or 10 to the negative 2. And then there are some auxiliary instructions here. And then in part C, you will be asked to derive the Richardson extrapolation formula that you derive for problem 1. Kailangan yung i-Richardson uli yan. I-derive nyo siya of order 2. Pero let's say, medyo madaya pala kasi hindi na kayo pinag-derive ng Richardson extrapolation. Kasi ito nga palang na-derive nyo sa problem number 1 ay order 2 rin. Tapos sabi ko, yung Richardson formula na d of yung bagong estimate ay equals to 4 d of h over 2 minus d of h all over 3. Pwede nyo itong gamitin sa kahit na anong formula of order 2. And lucky for you guys, problem 1 required you to use a formula of order 2. So ito rin yung gagamitin yung Richardson formula para dun sa differentiation technique na madederive nyo sa part 1. So yung d of h nyo dito or d of h over 2, kukomputin nyo following the formula you get from problem number 1. And then ulitin nyo daw yun with a perturbation process the same as in part B. Okay? So is that lab exercise clear? Aside from the perturbation magnitude, kayang-kaya na bang gawin? Okay, just a reminder, exercise 4 covers module 6 and 7. So baka kailangan yung i-review yung nasa module 6. But aside from that, do you guys have some questions or clarifications? Or naka-ready na yung unmute buttons nyo para magpaalam? Oh, yes. Who's that?
CK.
Oh, hi, CK. Do you have a question?
Ako po, sir. For number 2 po, sir, yung P, ang ipa-plug po ba na values ay 1?
Yeah. Kasi ang gagawin nyo ay estimate the yearly growth rate from 1790 to 1910. So ang maging idea rito ay kailangan yung gumawa ng table para kay 1790 hanggang 1910. Tapos ang step size daw ay 1. So gagawa kayo sa Excel ng 1790, 1791, 1792 hanggang 1910. Medyo marami-rami pala to. Tapos kukunin niyo yung P of T. I think na-gets ko na yung question ni CK. Ano yung i-plug in natin na T value here? I think the T value here is the number of years. So ibig sabihin, kasi ito ay 1790, 1850, and 1910. Can you guys try plugging in T equals say t equals 0 or t equals 1. Kasi hindi pala dinefine dun sa model kung ano si t. So what is t? Perhaps this is another thing I can verify with the lab instructor who wrote this problem. Kasi nga tama, hindi ko alam kung ano yung ipa-plugging ko sa t. Siya ba yung actual year number na 1790, or does 1790 correspond to t equals 1, or does it correspond to t equals 0? Alright? Para makuha niyo yung actual p of t value here. So baka posible na yung 1790 pala ay p of 0, or p of 1 yan, or p of 1790. Hindi natin sure. All right. So i-clarify ko na lang. So I'll make an announcement, or your lab instructors will announce this in your class on Monday. Okay? Then all the way down hanggang 1910, tapos 4-point backward. So posibleng kailangan ninyo para makuha si yung growth rate kay 1790, kailangan nyo yung data kay 1789, 1788, at 1787. Kasi kailangan nyo yung growth rate kay 1790, 4-point backward formula yung pinaderive sa inyo. So gagamitin nyo yung data kay 1790, data kay 1789, 1788, and 1787. Okay? Yeah, I'll just need to clarify that with the lab instructor concerned. Thank you, CK, for bringing that up. Mukhang nag-start na magsagot si CK, no? So I hope you guys will do the same. Other questions? Oh, yes, Lian.
Sir, ask ko lang po yung sa first question po kung kailangan pong ipakita yung derivation po ng formula, or kahit hindi na po.
Kailangan nyo ipakita yung derivation.
Okay.
Pero yun lang naman yung expansion, di ba, ni f of x minus h, f of x minus 2h, and so on. So
Yes.
medyo, pag mga ganun yung problem, pwede nyo i-treat literal yung instruction. Sabi dito ay derive. So kailangan nyo ipakita yung derivation. So
Okay
yun.
po. Thank you po,
Oh,
sir.
all right, you're welcome. Other questions?
Sir, may ka-clarify po ulit ako doon sa order 10 to the 4th. Sa order 10 to the 4th po, sir.
Okay.
Natanong ko po kasi, sir, sa inyo kung ang random numbers po ay from negative 10 to the 5th to 10 to the 5th. Kasi po dun sa module 5, yung sa perturbation po na order 10 to the negative, ang random numbers pa from negative 10 to the negative 1 to 10 to the negative 1. So I was wondering po kung yung random number ay mag-add po ng 1 dun sa exponent.
Yes. Kasi mangyayari ay dapat ang absolute value niya ay multiple ni 10 to the 4th, or multiple ni 10 to the negative, ano yung example? 10 to the negative, ano ba? 10 to the negative 4. So, ibig sabihin, yung size ng perturbation, yung absolute value ng perturbation ay hindi lalampas ng 10 to the negative 4. So, or a multiple of 10 to the negative 4. So, pwede itong 3 times 10 to the negative 4, 3 times 10 to the 1.3 times 10 to the negative 4, and so on. Ibig sabihin, magiging number siya sa pagitan ni 10 to the negative 10 to the negative 5 hanggang negative 10 to the negative 5 hanggang 10 to the negative 5. Though hindi naman siya ganun ka-strict, basta dapat yung absolute value niya ay papatak na ay a constant times 10 to the negative 4. Okay, is that fine, CK?
Bali, sir, yung random numbers po ay ano po, 10 to the, ano lang po siya, between negative 10 to the 4 to 10 to the 4th lang po, bali.
Yeah.
Plus or minus po kasi, di ba, sir, yung sa perturbation.
Yes. So ano siya, I mean, medyo may gray area doon. So kung ang order dapat ay 10 to the minus 4, so ibig sabihin, Ano ba ang 10 to the minus 4? Ang 10 to the minus 4 ay 10 times 10 to the negative 3. So, pero negative siya dapat, no? So, dapat 10 to the 4th. Actually, pwede nga siyang lumampas. Ano yung nilagay ko sa module 5? Sinama ko ba siya sa 10 to the negative 3 hanggang 10 to the negative 10 to the minus 3 hanggang 10 to the negative 3?
Sa module 4 ay module 5 po, sir. Sa module 5, ang nakalagay po, sir, 10 to, pag order 10 to the negative 2, ay yung random numbers mag-range po from negative 10 to the negative 1 to 10 to the negative 1.
Yeah, kasi mag-a-add ka ng 1 dun sa exponent kasi halimbawa dito sa example na to, pag kumuha ko ng number na nandito, ang order niya ay posibleng halimbawa negative 1.32 times 10 to the negative 4. Tama? Pag kumuha ko ng number na lampas dun sa 10 to the negative 4. Ang absolute value nito ay constant times 10 to the negative 4. So ito ay big O ni h to the ni 10 to the negative 4. So yeah, pwede mo siyang tingnan as mag-add ka ng isang exponent. Magpa-plus 1 ka dun sa exponent. So this would be 10 big O of 10 to the minus 4. Ganun din dito. So kung ang magnitude talaga ng perturbation ay 10 to the 4th, so you can pick a number or a random number between negative 10 to the 5th and 10 to the positive 10 to the 5th. Kasi pag kumuha ka dito ng number rito, for instance, si 3 times 10 to the 5th ay nasa loob nitong interval na to. Sorry, 10 to the 4th pala. 3 times 10 to the 4th. Okay? Pag kinuha mo yung big O ni 3 times 10 to the 4th, ang big O niya ay, or big O siya ni 10 to the 4th. So ito yung order, 10 to the 4th na sinasabi natin. Okay, so nag-a-add tayo ng exponent, tapos magkabilang side. Pwede kang mag-plus or mag-minus. Kasi nga random dapat yung perturbation o yung change dun sa data values. Okay? Medyo nalito rin ako dun ng konti. So mas okay nga na dinodrawing siya para mas clear yung meaning. Okay, is that fine, CK?
Opo, sir. Salamat po.
All right, other questions? Okay, so if there are none, then thank you guys for coming today. Enjoy the rest of your day. And as always, let's see each other again next week. Bye-bye, guys.
Thank you po, sir.
Thank you po, sir.
All right.